Hi, my name is Hannah Lohman, and I'm a member of the QSDsan group that uses quantitative sustainable design for sanitation and resource recovery systems. In the previous video, we covered the basics of life cycle assessment. And so in this video, we will discuss uncertainty and sensitivity analyses. So online in our Read the Docs, you can find this tutorial under uncertainty and sensitivity analyses. And so in this tutorial, we'll be covering two topics. In the first section, we'll discuss model, parameter, and metric. And then in the second section, we will discuss how to perform uncertainty and sensitivity analyses. And so first, we can check our version of QSDsan. And so here, the tutorial was made with 3.11, and I am using 3.12. So a little bit more recent of a version. And so in the first section, we will discuss model, parameter, and metric. So to perform uncertainty and sensitivity analyses, we first need to use the model class to establish a system model, and then we'll link it to the system we are interested in. So in section 1.1, we will create a simple system with TEA and LCA. So first, let's make a very simple system with a splitter, a heat exchanger, and a mixing tank. And so I will copy this code over. So from QSDsan, we'll be importing power utility and model. And if you're working on a version before 3.10, you can import this from BioSteam. And so then we can set our components by loading the default components, and then we can set our thermodynamics for the components, and then we can create two waste streams. So WW1 is our first waste stream, and we are using a COD influent model. And here we are labeling it as waste stream 1 with a 1000 flow. And then WW2, we are going to be using a BOD-based influent model. And again, we are going to set the ID to WW2 and then set the flow to 100. Okay, then we can set up our SAN units for the system. So we're just going to set SU to be QS.SAN units just to simplify our code and typing. And so S1, we will have that be our splitter. And so here we are setting the ID of this SAN unit to be S1. And then we are setting our influence to be WW1, so that first waste stream we created. And then everything coming out of the splitter will be one flow will be to the heat exchanger, so we'll call it 2HX. And then the other one will be to the mixer, so we'll call it 2mixer. And then we can set the ratio for the split. So 20% will go to the heat exchanger, and then 80% will go to the mixer. And then our second SAN unit will be H1, which is our heat exchanger. And so again, we set the ID, we set the influence streams, and then we can set additional features. So here we're setting the temperature of the heat exchanger. And then we can also create the mix tank where we have, again, the ID of the mix tank, influence, and then setting tau to be 2. Then we can create our system using all of these SAN units we developed. And so we are going to ID it as sys, just for system. And then we are going to include the 3 SAN units in the path that we created. Then we can use .simulate to simulate the system we just created. And then we can also see the diagram. So here, this is a good way to check to make sure everything is connected how you want them to connect. But we can see that we have our 2 waste streams, the 3 SAN units, the appropriate split from the splitter, and then streams coming out of both the mix tank and the heat exchanger. So now we can add some stream costs for the TEA. And so here we can use the .price attribute just to set the price of the first waste stream and the second waste stream. So here we're just setting it to 10 cents, 0.1 US dollars. And then we can also create our TEA using the simple TEA that we learned about in the TEA tutorial video. And then we identified that we want it for the system that we just created. And we can also set the lifetime. So here we're setting the lifetime to be 10 years. Then we can also add some stream impacts for the LCA. And so here we're going to set the global warming potential impact indicator. And so here we are going to use the impact indicator class. And then here we are identifying that we want it to be global warming potential as the ID, and then the unit will be kilograms of CO2. And so now we can set the stream impact for the first waste stream. So waste stream item 1, the stream impact is going to be ID'd WW item 1, and then we can set what stream it's linked to. So here we're setting the stream to be linked to the first wastewater stream. And then we're setting the global warming potential to be 0.1, so 0.1 kilograms of CO2. And then we can also set the same for the second waste stream. And we can use the .copy attribute to just copy the first waste stream. And then here we're setting the ID to be WW item 2. And then the stream is waste stream 2. So here we're saying, let's copy what we just did above and apply it to waste stream 2. So now we can consider some construction impacts. And so here we're just going to assume that we need 5,000 kilograms of stainless steel per meter cubed of reactor. And we also know that the impact is 4 kilograms of CO2 per kilogram of stainless steel. So here we can set stainless steel, the stainless steel impact item. So here we're going to call it stainless steel. The functional unit will be in kilograms, and then we can set the global warming potential to be 4. So here we know that we have 4 kilograms of CO2 per kilogram of stainless steel. And then we can set this for the mixer that we created. So M1 stainless steel, construction of the mixer. And so we are going to set this construction to be M1 underscore SS, and then the item will be the stainless steel that we identified above. And then we are going to do M1.construction and just set it equal to what we just created. And we want to keep this comma at the end just so we can add, potentially add future objects to this in the future. If we don't have the comma, then we can't add on anything into this list. And so instead of making a subclass of mixed tank to add impacts, we can also just do it on the fly. And so if I copy this code over, so here we're going to set old mixed tank 1 design to be M1._design, and then we can decide, we can define a new method where we are going to name it new M1 design. And then here we can call the origin design method, which was old M1 design. And then here we can set the M1 underscore stainless steel quantity to be the M1 design results, the total volume of the reactor, and then multiply it by 5,000 because that was the assumed density of stainless steel per meter cubed of reactor. So we have 5,000 kilograms of stainless steel, per meter cubed volume of reactor. And then we can add the construction in this way. And so then we can pass this line, or in this line, we pass the new design method to M1. Now we can add in the impacts for electricity. And so here we're setting the impact item of electricity, and the functional unit will be in kilowatt hour. And then the global warming potential for electricity is 0.1 kilograms of CO2 per kilowatt hour of electricity. And then we can make the LCA. So here we are going to make the LCA using the LCA class. The system identified will be the system that we created, and the lifetime is 10 years. And then we also have electricity in kilowatt hours per year. So we want to multiply the electricity consumption by the lifetime. And so here we're going to get the electricity consumption for the system, and then we're multiplying it by 10 for the lifetime. Okay, so next we are going to create a system model and add uncertainty parameters and metrics. So the model class is used to enable uncertainty and sensitivity analyses. So we need to first create the model for our system. And so here we are going to set model to be model of the system. And here we're using the model class. And then uncertainty parameters can be added using the model.parameter method. So let's assume we're unsure of the price of wastewater, electricity, and the impact characterization factor of stainless steel and electricity, as well as the split ratio of the splitter and the temperature of the heat exchanger. So all of those will be our uncertain parameters for this tutorial. So we can use the package QSDsan to create the distributions. And so here we are going to import the distributions as shape from QSDsan. So there are multiple ways we can use the parameter method, but we like to use the following one. So here we are going to set param to be model.parameter just to shorten our coding. And then we're going to set distribution, so the distribution that we're going to use. And we will do shape.uniform. So we're going to use a uniform uncertainty distribution. And for that, we need to know the lower and upper values for the parameter of interest. And so in this case, we are interested in the wastewater price parameter. And so we will use our parameter and we'll name it wastewater price. And then we have to tell it what element we're looking at. And so here we're looking at the TEA, and the element just determines which portion of the system will be simulated. So we want to simulate the TEA when we're changing the wastewater price. And then kind determines whether the value will be included in the simulation. And so here we're setting the kind to be isolated, and then we're identifying the units to be US dollars per kilogram. And then we set the baseline to be the WW1.price, and then the distribution is the distribution that we defined above. And then we can set a method to actually set the wastewater price. And so here, set wastewater price is a setter function that will update the price. And so set wastewater price, I is the input, and then wastewater price 1 and wastewater price 2, again, we had them equal above, so we're having them equal here. And we're going to have it set to I, which will be the value in our distribution, depending on how many times we run the simulation. And so another way to add parameters is using this way to do it. And so here we can set the baseline to be the power utility price. And then we want to identify the distribution we plan on using. So we want to use a triangle distribution for power utility price. And so for a triangle distribution, we need to know the lower value of the triangle. So that will be baseline times 0.9. So we're doing a plus or minus 10% range. The midpoint will be the peak of the triangle. And so here that will be our baseline value. And then the farmost corner of the triangle will be the upper. So that will be baseline times 1.1. So 10% higher than the baseline value. Then we can create a setter function. So we are going to set the E setter similar to above. We will set the power utility price to be I, so whatever value in the thousands of values that we have for this distribution. And then we can use this where we have the parameter, and so we'll identify what setter we will use. So here we'll use E setter, the setter function. The name of the parameter is electricity price. The kind of the parameter will be isolated. The element, so what portion of the system we want to run, will be TEA. Units will be US dollars per kilowatt hour. And then we set the baseline to be baseline. Distribution is dist, so the distribution we identified above. And so kind of similar setup up here, just we are first identifying the setter function and then calling everything for the parameter below. Okay, so now we can do the impact factors. And so here we wanted to have uncertainty around the stainless steel impact factor as well as the electricity impact factor. And so here our baseline first for stainless steel will be the stainless steel characterization factor, global warming potential. The distribution for this will be a uniform distribution with plus 10% and minus 10% on either end of the baseline. So the lower point of the distribution will be baseline times 0.9, and the upper will be baseline times 1.1 to get that plus and minus 10%. And then for our parameter, we will be using the stainless steel global warming potential as the name. The element that we want to look at will be the life cycle assessment LCA portion of our simulation. This parameter will be an isolated parameter. The units are kilograms of CO2 per kilogram of stainless steel. And then we can set the baseline and the distribution, how we defined above. And then our setter function, similar format where we can set the stainless steel impact factor using all of the values in our distribution. And then similarly, we can do the same for the electricity global warming potential. Again, for this, we are also doing a uniform distribution with plus and minus 10% on either end. And then these are all very similar to what we did above for stainless steel. And again, we have a setter function for the electricity impact factor. And then finally, we are interested in the uncertainty of the split ratio and the heat exchanger temperature. And so for these two parameters, we need the kind to be coupled. So that means it will affect both the mass and energy balances. So we will need to rerun the whole system, the mass and energy balances, instead of just an isolated where we only have to run the TEA or LCA without redoing the mass and energy balances. And so for the split ratio, we are going to assume a triangular distribution. And the lower will be 0.1, the midpoint will be 0.2, which is what we originally had the split set at above. And then the upper value will be 0.3. And then for the parameter, we will call it S1 split. The element that we'll be using is S1, so the splitter. The kind for this parameter is coupled. So again, we need to rerun the system mass and energy balances with this parameter. There are no units for this. It's just a ratio. And then we set the baseline and the distribution. And then we can set the setter function where we will be able to change the split value every time we run the model. And then similarly for the heat exchanger temperature, so we will have the baseline be just the original temperature we had selected for the heat exchanger. And additionally, the midpoint doesn't have to be the same as the baseline. So if your triangular distribution is lopsided or you don't want the baseline to be the same as the midpoint, you can change it to be however you want. And so here we will have the midpoint to be slightly different than the baseline. And so we'll have the lower be baseline -5, midpoint will have it be 1 degree higher than the baseline, and then the upper will be the baseline times 1.1. So however your triangular distribution is, you can do whatever you want with it, whatever makes sense for your system. And then we can have the parameter. So we will have the name of the parameter be H1 temperature. The element that we are dealing with is the heat exchanger, so H1. And then the parameter will be a coupled parameter. We have identified the units as degrees Celsius, and then we can set the baseline and the distribution. And then again, we have a setter function to set the temperature. Okay, so now we can add the metrics. And so we are interested in net earnings for the TEA and then the total global warming potential for the LCA. And so the metrics are just like the results, final results that we want to see. And so here we're going to set, so here we can have metric is model.metric, and then we can set the metrics that we want to see. So here we want the net earning, so that is related to the TEA. The units are US dollars per year, the element is TEA, and then we can define the net annual or get annual net earnings, and it will return the net earnings of the TEA. And then similarly, how we did it above, there's a different way you can do this too. And so first we can define the method get annual global warming potential. We'll tell it what to return. So we want the total impacts of global warming potential of the LCA divided by the lifetime of the LCA. So we want kilograms of CO2 per year. And then we can define the metric. So we will have the getter function. So getter just means we're going to get this value as opposed to setter where we're setting a value. And so the getter will be getting the get annual global warming potential. The name of the metric will be GWP. The units of the metric will be kilograms of CO2 per year, and then the element will be LCA, life cycle assessment. Okay, so now we will perform the uncertainty and sensitivity analyses. And so first we will do the uncertainty analysis. And so now that we have the model, we can do Monte Carlo. So first we can import NumPy as NP, and then we are going to get set a seed. This basically will mean that all of the values that you simulate and perform, so if we're doing 100 simulations, having a seed means that you will get the exact same sample. If you don't have a seed, those 100 numbers will change depending on when you run the simulation. And so it's really important to have the same samples for the sensitivity part of this tutorial. And so after we have our seed, it will just be a random number. We are going to perform 100 simulations. And so here we can set our sample size or sample. So we're going to have n equals 100 simulations, and we will do Latin hypercube sampling. And so if you want, you can see what options you have as far as what type of sampling method you want to do. But for most of our work, we always use Latin hypercube sampling. And then we can load our samples. Then we can do the simulation using model.evaluate. And then we can look at our parameter values and the metric results stored in the table attribute. So here we have our variables that we varied originally. And so we changed the splitter ratio, so you can see the values are all different in the range that we set above for the splitter. We have different temperatures every time we run the simulation. We're varying our wastewater price between 0.5 and 0.15. Electricity price has been varied. Impact factors for global warming potential for stainless steel and electricity. And then we have our metrics that we wanted. So we said we wanted to see the net earning in US dollars per year. And then we also wanted to see the global warming potential each year. So this table is really nice just to see a summary of what your uncertainty analysis looks like. And it's also really good for when you want to take this data and make figures, report it in your papers, whatever you're using this uncertainty analysis for. And so we can clean up the results. So if you want certain figures or anything. And so here we're going to use pandas, and we can define a function to organize the results. And so here we're going to have our model and a path. And then we can have the length of our model parameters, so the number of parameters that we're using. And then we can kind of create our table with any number of rows and then all the way up to the length of the model parameters. Yeah, we can also calculate percentiles. So if we use the quantile, we can calculate the lowest value, highest value, 5th, 25th, median, 75th, and 95th percentiles. And then you can use Excel Writer to put the parameters onto a sheet in your Excel spreadsheet called parameters. You can create a new sheet for the results, and then you can also create a new sheet for the percentiles. Okay, so then if we actually want to see the spreadsheet that we created, we can run this. And then the Excel spreadsheet example model. So again, we have one tab for the parameters and all of the 100 values that we simulated, the results, and then a summary tab with the percentiles for the two metrics of interest. So we can also take a quick look at the results by using functions in the stats module. And so we can create some figures. So here we can have two box plots for both the net earnings and global warming potentials. And this plots the uncertainties. We can also do a kernel density plot to see the values. So here we're saying the x-axis will be the model metrics, the first model metric, so net earning. The y-axis will be the second model metric of interest, which was the global warming potential. We are going to do a kernel density plot, and then we are going to fill the plot. So here we can see our kernel density plot and the uncertainty distributions for each metric of interest. Then for the sensitivity analysis, QSDsan has the following functions for sensitivity analysis. So for the correlations, we can do Spearman correlation, Pearson, Kendall, KS. We also have Morris analysis. There's also Morris-Till convergence to increase the trajectory number until the results reach the set criterion or the trajectory number reaches the set maximum. We can do FAST analysis for Fourier amplitude sensitivity test or random balance design, RBD FAST. And then we also have Sobel analysis. So depending on what type of sensitivity you want to do, we have all of these within QSDsan. And so for each of these methods, there is a corresponding plot XXX. This example would be plot correlations, or for get correlations method for visualizing the results. And so if we want to do Spearman, the documentation page of stats does have some good examples, but we can do one here. And so RDF and PDF are the data frames containing the sensitivity indices and the p-values. And so we'll say RDF and PDF are the sensitivity indices and the p-values when we run the Spearman correlation for the model. And so now that we have those data frames, we can display the results of the sensitivity. And so we can see the price of wastewater driving the cost, and the characterization factor of stainless steel will drive the impact. So let's see, price of wastewater has a -1, so very strong correlation. The correlation will range between -1 and 1, where any values closer to the extremes of 1 and -1 will drive the sensitivity. And then, yes, so stainless steel global warming potential for the LCA is 0.77, which is much higher than 0.18. So this is a much stronger correlation than the electricity global warming potential. And these values are essentially 0. They shouldn't be influencing the TEA. So you can assume these are 0. Same with our prices. The price shouldn't drive the life cycle assessment. Then we can also create a bubble plot to show these results. And so here, the size of the bubble means it is higher correlated. Bigger bubbles means stronger correlation. Smaller bubbles means less strong of a correlation. And then the colors, so blue represents a negative correlation, where red would be a higher or a positive correlation. And so this is the end of our tutorial. And I hope that you found it helpful, and I hope that you will be able to incorporate sensitivity and uncertainty in your use of QSDsan. And we really want you to take advantage of going through these tutorials to get more familiar with the documentation in QSDsan.